Hello everyone. So today we're going to go over section 11.1, exploring rational functions using transformations. So in example 1, we're going to sketch the function y equals 1 over x, and we're going to do so by using a table of values. And we can simply find the reciprocal of each of the x values. So negative 1 over 2, negative 1, negative 2, 2, 1 and a half. Now, when x is equal to 0, its reciprocal is undefined. Which means x equals 0 will be a non-permissible value. Or that x cannot be equal to 0. So if we were to plot the points in our table of values, we will get the graph on the left-hand side, right here. Notice that as x approaches 0 from one side, the values of y will keep increasing, and as x approaches infinity, the y values will continue to decrease, but always staying positive. So let's say, for example, when x is equal to 100, its reciprocal will be 1 over 100, which is a very small number, and that will continue on as x approaches infinity. So the same thing is going to happen on the left-hand side of the graph as well. So here, these values will stay negative but approach 0. These values will approach negative infinity as x approaches 0 from that side. As a result, we have two asymptotes, one that is vertical and one that's horizontal. Okay, so here we have the vertical asymptote x equals 0, and the horizontal asymptote y equals 0. And we also can now write the domain and range for this function. The domain is x is an element of the real numbers except for 0, because that is a non-permissible value. The range is very similar. Y is an element of the real numbers, but once again, not 0. So next we have example 2, a transform form of example number 1. So there are 3 transformations that we're looking at. The first is this 4 here, which is going to be a vertical stretch by a factor of 4. The second is this plus 1 here, which will shift the graph left 1 space. And finally, we have a plus 5, which translates the graph up 5 spaces. And this is the resulting graph if we were to use a table of values. And using a bit of symmetry after we add in the asymptotes. So the asymptotes from the previous graph, x equals 0 and y equals 0, will be translated. That is to say, the first asymptote, x equals 0, will be translated 1 space to the left and become x equal to negative 1. Likewise, the horizontal asymptote of y equals 0 will move up 5 spaces and become y equals 5. Okay. So just as how the previous example, there was a line of symmetry along this diagonal, we can use that symmetry to draw the second graph. Which is what we have done here. It's also possible to draw this graph using a table of values or a table of transformations. Okay, so for this graph, the non-permissible value is just x cannot be -1. The asymptotes, x equals -1, and horizontally, y equals 5. And for the domain and range, we have the corresponding values. X cannot be equal to -1, and y cannot be equal to 5. So in general, if we're given y equals to a over x minus h plus k, then we know that the vertical asymptote is going to be x equal to h, and the horizontal asymptote is y equals k. And a is the vertical stretch, and of course, if a is less than 0, we also have a reflection over the over the x-axis. Okay, let's continue. Example 3. Right, so before that, a rational function is a function that can be written as a quotient of two polynomials, so p of x and q of x in this case, right here, where q of x is not 0 because otherwise we will be dividing by 0. So in our first rational function example, that looks a little bit different than before. We have 4x minus 10 over x minus 3 in example 3. The sketch is already there, but how do we make the sketch? Well, we need to consider that y is also equal to 4x minus 10 divided by x minus 3. So we can actually divide these two polynomials using synthetic division. So here we have it on the right here. The numbers are 4 and -10. And on the left-hand side, we have a 3. So the first step, the 4 gets carried down. 3 times 4 is 12. -10 plus 12 is 2. So the 4 gives us the quotient part. And the 2 is the remainder. So what that means is we can write 4x minus 10 which is the dividend, as the quotient times the divisor plus the remainder. So a very standard division statement. But we are not looking for 4x minus 10. We are looking for 4x minus 10 over x minus 3. So we're going to divide every term by x minus 3. So the left-hand side and the two terms on the right-hand side will each need to be divided by x minus 3. So, and then we can simplify the expression. So on the left-hand side, we just have 4x minus 10 over x minus 3. Sorry, that's a different blue. And then the second term, sorry, on the right-hand side, we have 4, of course, because the x minus 3 will eliminate each other. And then plus 2 over x minus 3. So to summarize what we have done is we have rewritten 4x minus 10 over x minus 3 as 2 over x minus 3 plus 4. Oops, sorry about that. And of course, that means we have something just like the previous example. We have a vertical stretch by 2. The graph is moved right 3 spaces and up 4 spaces. So we can find our asymptotes. X equals 3 and y equals 4. Okay. Of course, x cannot be equal to 3. That is still the non-permissible value for this function. And y equals 4 is the horizontal asymptote. Okay, so go ahead and write this here. And we have the corresponding domain and range of this graph. Okay, so additional points of accuracy can be found using X and Y intercepts. So in this case, we can just let y equal 0. So we just have 4x minus 10 over x minus 3. Which of course means that 0 is equal to just 4x minus 10. And we can solve for x and get that x is equal to 5 over 2. We will add 10 to both sides and divide both sides by 4. So we get 5 over 2. Likewise, we can find the y-intercept by letting x equal 0. So we have 4 times 0 minus 10 divided by 0 minus 3. And so y-intercept would be just 10 over 3. And those 2 points are reflected on the graph here and on the right here. And of course, the additional points were found using a table of values. And the graph was drawn by a combination of the different points and also the asymptotes. Okay. So in example number 4, we're going to be given the graph and we're going to find the equation in the form y equals a over x minus h plus k. So in this kind of question, usually the asymptotes would just be integers. So in this case, we have x equals 4 for the vertical asymptote, and y equals to 7 for the horizontal asymptote. So we will know that h is equal to 4 and k is equal to 7. After that, to find the a value, notice that if there were no vertical stretch, this is where the point corresponding to 1, 1 would be. But instead, the point is up here. So that is 1, 2, 3, 4, 5 times the height. That means we had a vertical stretch by a factor of 5. Combining all of that together gives us the following, and that is the function would have been y is equal to 5 for the vertical stretch over x minus 4 and then plus 7. X minus 4 and plus 7. Okay. So in the last two examples, we're going to look at rational functions with a quadratic expression in the denominator. First one is the simplest case, just y equals to 1 over x squared. Okay, of course, the graph is once again drawn beforehand. I'm just going to go ahead and complete the table of values to check the value, check that it was drawn correctly. So -2 squared is 4. The reciprocal is a quarter. And then we have 1. And then we have 4. 4, 1, and a quarter. So what we notice is that there are no negative values for y that are possible because the x values is always squared, so that makes it positive, and then the reciprocal will still be a positive number. We do get the non-permissible value of x cannot be 0, similar to the first example. So once the points are drawn, we can see that some of the behaviors are like example 1. So for example, there's an asymptote at x equals 0. Since if the x values approach 0 from either side, they'll increase, but they will never be 0 because of the non-permissible value here. And we also have a horizontal asymptote at y equals 0. Since what happens as the x values get very, very large or very, very negatively large is that they'll be squared, and then we take a reciprocal, which makes them very small values, but positive. So we have x equals 0 and y equals 0 for our asymptotes. One thing to notice is the domain and range. The domain will be x is not equal to 0. The range, however, will be y is greater than 0. Notice that y is never negative or 0. One last example. So this is about transformation still. So we have y equals to 5 over x squared plus 2x plus 1, and then plus 2 after that. So we can go ahead and factor the denominator. And what we would notice is that the denominator is actually just x plus 1 squared. So we actually can rewrite the function as 5 over x plus 1 all squared, and then plus 2. Meaning that we have 3 transformations. The first one is a vertical stretch by a factor of 5. And then we move the graph left 1 space, and finally up 2 spaces. So we expect the graph to have the same shape as the one in example number 5, but with those changes. And of course, now we can draw in the asymptotes. Okay, so, sorry about that. And then y equals 2. So x equals to -1 and y equals 2 are asymptotes. So a good question at this point may be, how do we know which points or which x values to choose to use a table of values? And we usually want to choose points that are next to our vertical asymptote. So for example, in this case, our asymptote is at -1, so we can choose like x equals 0 here, or x equals -2. And each one of these will give us 7. And if we move 2 spaces to the left or the right of the asymptote, we can get the points 1 and 3¼ and also -3, 3¼ So these points are meant to be slightly above y equals 3, but it wasn't drawing, sorry, they weren't drawing particularly accurately. So from here, we can find the x-intercepts and y-intercept. Notice that the graph doesn't actually have any x-intercept, and if we were to try to find them algebraically, so we let x equal 0, you can see what happens. Oh, sorry. And then we have -2 is equal to 5 over x plus 1 squared, which of course gives no solution because the expression on the right-hand side will always have to be positive. And then the y-intercept, if we let x equal 0, we have 0 plus 1 squared, which is just 1. 5 over 1 is 5, and then plus 2 gives us 7, which is this point right here. Okay, so for this graph, the domain, x cannot be equal to -1, and then the range, y is greater than 2. So that's it. We have looked at a few rational functions by looking at transformations of both y equals 1 over x and also y equals to 1 over x squared. And then we examine a few different types of asymptotes. And that's it for today, so thank you for listening.